Excuse me, Professor.
Yes.
Please, actually, what I have to say is not really a question.
Sorry, who is asking a question? Can you use this? Show yourself, please.
Yeah.
Can you turn the video on when you ask a question?
My video is turned on already. Can you see me?
Hi. You have a question, you said?
Yeah, what I want to say is not really a question. I just want to request something from you, please. My colleagues and I, we are joining the class from Kigali, and we have not had a course in particle physics. So I just want to implore you, if there are some concepts that you discuss that will require knowledge of particle physics, can you please occasionally just, brush it through for us, because we won't like to be stopping you at every point in time that we don't understand. I don't know if you get my point.
What the best thing you can do is to come for the office hours, and we go through the thing. We are going to have office hours. Or you are asking me to, maybe I didn't understand what you were asking me. Sorry. Try again.
Like the point I'm trying to make is this: if there are some concepts, or there are concepts which you'll be dealing with in this course that will require the knowledge of particle physics, I'm just saying my colleagues.
Yes, sorry, go on. Yes.
And I, over here in Kigali, we haven't had a course in particle physics that will appreciate if you could just.
If I could just.
If you could just occasionally, just give us like just brush it up for us, so that we actually understand the concept that has been discussed, and we don't want to be stopping you every moment.
That's impossible. This I cannot. Let's see what I can do. I can't do that because I don't know what you don't know. You see, when you teach, the thing about teaching, the whole thing for someone like me is preparation. Now, what is the preparation? Is the selection. I could start speaking now, and I can speak till 8 o'clock in the evening, and I won't get tired. I got so much to say. So what I do before the lecture, I try to select between all the things that I have to say, which actually have to do with the course. So now I cannot do yet another one. What you can do, you just feel free. You just interrupt me at any point, and I tell you, I'm sorry, this is really too far. I'll suggest you some reading, or I even try to give you a concise. I have no problem. Let me put it this way. I'm a real-time teacher, unusual in this sense. I could change my course now. If the whole audience told me, look, you're going over our heads, we should really teach us what the pion is or something, I'd sit down and I'll teach you what the pion is. So just feel free, you and whoever, that no matter how basics you are, because I can't think what is it that they should know. You see, this is the hard thing. I will have to prepare for that. But by the way, I don't really know what Smirnov does. We have a course on that, but I don't, I sort of talk to him, but I don't really know. So I can think, of course, of something you should read. By the way, the book that I suggested, Hazen and Martin, has some particle physics to start with in the beginning. It's a pedagogical course. I'll suggest you maybe even a more pedagogical book to have a look. But once again, you guys feel free to, please, this is for all of you, that you may be thinking that this question is not appropriate for the course. Any question is okay.
All right, thank you for your warm
reply. I have no problem being interrupted. If it's okay. I've just finished. And between the courses I was teaching at the LMU University in Germany, there were a lot of questions, and I just loved it. There were moments when there would be a question after question. Any other question, please? We'll start. Every question, every lecture starts with questions. Okay. The first thing I want to make sure that you guys are keeping up with me.
Yes, Professor, I have a question. The last part in the previous lecture, we were talking about what happens if Y is proportional to Q electromagnetic. And we said that if this happens, then the charge of the neutrino
Right.
and the charge of the electron must be equal.
Right.
This is because we are dealing in the fundamental representation of SU2, right?
Very good. Very good.
What happens if we are
No,
dealing
not because it's fundamental. No, very good. The question is posed. So let me answer it. So this is good. This is a very good question. I'm glad you asked, because when I said it, I hoped I could see it. You may understand it, you may not understand it. Remember, if you don't ask questions, I won't go on. I make statements. Okay, this is very important for you guys. I make statements that somehow could be clear, but not necessarily. So it's crucial. Oh, sorry, I'm here. And what is it? Lecture 3. Today is lecture 3. So I prepared this. So let's start. Very good. I was gonna repeat what I said last time anyway, but this way we'll make sure this is done. So we said yesterday, this question really fits to how I wanted to state. So the G standard model, we concluded yesterday, SU2 was not enough. The G standard model minimal must be SU2. Now look what I'm going to write. I'm going to call it SU2L to remind you that only left-handed fermions can know about it, SU2. SU2 means weak interactions. Only left-handed fermions have weak interactions. Then there is U1. I will give it a name. We call it U1 hypercharge. Okay, this is the celebrated 1961 paper. This is the beginning of the standard model. Everything is, all the physics of the gauge series here in the Glashow's paper. What is not is the Higgs mechanism, to be introduced later by Weinberg and Salam. And of course, it is a profound next step. But I want you to remember, get a rough feeling of the years when this was developing. Okay, your numbers may not be so important. So what we said here, so before I come to the question, let's now systematically, it's actually today where we are really becoming systematic. And we have to stop being systematic, because I was just told that there are some of you who don't know particle physics, and you'll be free to ask, and I will then, in a not systematic manner, go over some of the fundamentals. So what do I mean when I say that there is SU2L? I mean that there is a quark doublet, which I call UDL. Notice I'm pretending that there is just one generation. I'm sure all of you know that there are more generations, but who cares? There are 0 copies of the first one. In order to understand the basics, the fundamental, the core, the essence, we have to start always as simply as possible and build up on complexities. There is also a left-handed doublet. So you see, I fix the gauge group. This is very important. Then I choose the matter. The matter, we call it. Matter is fermions. Why? Because matter is made out of fermions, which is quarks and leptons. This is new EL. These are the guys that know about SU2L. This gauge group have their couplings. We decided to call them a G and G prime in a not a very imaginative manner. There are also right-handed fermions. Remember, we said yesterday or the other day, they are all left and right. They, however, may behave differently. So I should not forget that there is the right-handed up quark, a right-handed down quark. They are singlets. Notice the way I'm writing now. There is a right-handed electron. Okay. There will be a question throughout the time, is there not a right-handed neutrino? Nobody had ever seen it. The standard model is a theory of observed particle and phenomena. So the fathers of the standard model emphatically make a theory without this. Let's even cross it. We don't even want to know what it is. These are the particles that has been observed in nature. And these are the particles that made the whole universe. Everything in this world is made out of these particles. Proton is UUD. I just made a proton. Once I made a neutron, which is UDD. Remember, this fixes the charges. Q up is 2/3. Q down is -1/3. From the fact that Q proton is 0, oops, 1, and Q neutron is 0. I can put them in parentheses. These are particles that are composites. They are not elementary. The elementary particles are the ions that I have specified here. Okay, so when I say SU2L, before I even answer what the group is SU2, what I mean in this group, so the meaning of this SU2L. So we say that the group is SU2L. What does that mean? It means that the generators, there are generators we checked on left-handed fermions. Let me call it TAL. They are Pauli matrices. So in other words, what I could write, there is some kind of operator that, let me put it ahead, that acts, for example, on LL. This acts as TAL, of course, which is LL, which is sigma A over 2. The same operator acts on QL. I call them TAL. They must be the same. The group is universal. The beauty of group theory is universality. Every representation has the same behavior. So if I say that this is a doublet UD, whether it's up and down quark or neutrino and electron, of course, the behavior is the same. What about the right-handed? What would be TAR? I should write here. And TAR is, someone wants to tell me what would be the form of the generator on the right-handed fermions? Someone likes to venture into this? I pause, I give you a chance.
Is it identity?
No. Almost true. 0. You meant correctly, I'm pretty sure. I mean, remember, U, the SU2 transformation belonging to U is E, theta A, and we write here TA. Now I wrote generically. So the question that I was asked, TA, for the fundamental representation is a Pauli matrix. If I take a triplet, that would be 3 times 3 matrix and so on. So on a thing, I think what you meant that on the right-handed fermion, U is 1 identity. You probably meant that. So in other words, what we said that LL transforms as E to the I theta. Let me write once more. A sigma A over 2 LL. This is the meaning of the above equation. So when I say that TR is 0, what I mean it's a singlet. It cannot be identity, it must be 0, because what does it mean it's a singlet? It doesn't even know that there is an SU2 group. A right-handed electron is just like you and me. We don't care that there is SU2. You and I don't transform under SU2, right? We don't have our, SU2 partners, okay? Electron, it just simply, it has to stay itself, okay? So what I mean is that ER, to be precise, transforms into ER under SU2L. That's the meaning. UR transform into UR, DR transform into DR. So this is equivalent that U in the above cases is 1, which then means that TA, well, why don't I write immediately that TAR is 0. In other words, TA, this kind of generic thing acting as say ER is 0. TA acting on UR is 0, and so on. Okay, I don't have to keep writing. This is the meaning of SU2L. Next step is we said that there is U1, and when I said that the group is SU2L, now has this meaning times U1. That means that TA hypercharge is 0. And let me write here the head for any representation. Fundamental, spin 1. I mean spin, when I say spin, I mean the weak isospin, this, whatever. You can imagine a representation which has T3, I don't know, 5/2 or something. They simply commute. This is the meaning. There is an equivalency of these two meanings. Which means, so you see, take two fields which are up and down. Up and down may be up and down quark. Sometimes by up and down, I will mean up and down quark. And sometimes I will mean just upper and lower component, which is the same. Please remember that as far as the weak interaction is concerned, there is no difference between up quark and the neutrino. They are the same particle for this, messenger, which is called the W boson. W boson doesn't care at all. If you're left-handed, this funny guy interacts with you. Doesn't care what charge you carry. By the way, as you know, quarks also carry color that we will be talking about, okay, from time to time. But now it's not something that I need to think about because I speak of weak interactions. They're also spinners. Each of the particles here in a doublet is a spinner. I suppress the Lorentz index. I just think of the SU2 properties. Okay, that's very important. So U and D, you see what the SU2 does. SU2 generator takes you from up to down, right? There is, for example, a generator which we call T1, which is sigma 1 matrix. And that takes precisely exchange up and down. It's off diagonal, as you know. And when I say that TA is 0, that means immediately that hypercharge of the up must be equal of the hypercharge of the down. Otherwise, how could you stay within the, how would they commute? This is the meaning, by the way. This is what I mean that they commute. This is precisely the meaning. This is the question I was asked, and I'm posing here to make sure that you guys are following. You see, imagine that you imagine. So let's say, I say they are different. Okay. But then I take a rotation, and it has to stay the same. UD can go into DU under this T1. Agreed? That's precisely what it does. But hypercharge should not know about it. Hypercharge commutes with this group. Hypercharge cannot be inside the group. I'm not allowed now. You see what I would do? Now down becomes up. So I said, for example, here, let's take Yukawa up is 1. It's some number, and Yukawa down is 2. But if it commutes hypercharged with this, the situation at the end of the day should be the same. This is somehow group theory. You see what is interesting, the question, okay, I always find this, by the way. I find that I have to make you understand what group theory is. I find that you guys have a group theory course, learn the fancy aspects of group theory, but do not have the SU2 in your fingers, okay? I'm gonna make sure that at the end of the course, I don't give a damn that you know sophisticated group theory. I want you to understand, for example, group theory means that this is just a name, up and down. There is no up and down. Look, I can make up and down become down and up. It's just, group theory says that there is an invariance under these transformations, okay? Everybody is equal to everybody else inside the group. Their T3 numbers are different. That's how I organize it. But I'm allowed to move inside the group. So from here, you see now these down is up. So from here I would conclude here that Yukawa down must be 2, because that's an upper component, and Yukawa up must be 1. When I say Yukawa up, who is this guy up? Are you getting this? This is a fundamental concept. That in the SU2 for W doesn't care whether you're up and down or whatever, whether you're a neutrino or an electron. That's the meaning of group theory. This invariance under rotations inside the representations we are talking about. So obviously the only way to make this be consistent is that hypercharge. We have the same notation later for Yukawas, forget it. Hypercharge now. The only consistent, this is the consistency of the group transformations of SU2. This means that commute. By the way, I also mean that the group is like this. There is times Lorentz. Lorentz commutes with these things. I'm not talking now about the Lorentz group, okay? The other day I did, because I was interested in what happens when I just take the up particle and I make Lorentz transformation on it. But this is very important, Lorentz is outside. Which means, for example, when I say that the group is SU2L times Lorentz, okay, just to appreciate, what does that mean? That means that if the upper component is left-handed, so must be the down component, because there is no difference between an up. I cannot write like this. This is forbidden, because it would not commute with Lorentz. I would break the Lorentz symmetry. Like here, I would break the hypercharge invariance, because suddenly the down quark, which had 2, became an up quark, which you have 1, okay? And the invariance would disappear. Instead, the meaning of Lorentz is that if you have a multiplet, they must have the same chirality. So for example, if I have a larger representation, nothing to do with the doublets, I have a larger representation which has a dimension 5, I don't know, or representation 127, or 10 billions, you know, there is particle F1, F2, F3, you tell me how big you want it, they must be all left-handed. If one is left-handed, they must be all left-handed, or there may be all right-handed, F1 prime, F2 prime, some other number. They may be all right-handed, but never F1L, F2R, and so on. This is the meaning of the direct product. I'm taking my time to explain this fundamental concept, and I'm also showing you how your questions will help you understand what is going on. You got to stop me at every point. When the statement that I made here, by the way, you should have it clear immediately from your knowledge of group theory, okay? But as I tell you, don't feel bad. I guarantee you that most of you did not really learn group theory the way you thought. Okay, I'll find out. I will be asking questions of group theory to prove the statement I'm making. I've been, you know, around for a while, so I could see this. This is sort of statistically quite true. Is this clear now, please? I can't have you. It's a fundamental point. And now you understand the art of teaching and listening to a teacher, okay? That presumably you knew, is that I will make statements that you are supposed to know. Supposed to know doesn't mean that you know them. You are free to ask again. But did I explain this? Is it clear now?
Yes, thank you.
Good. Any other question as I'm here? I'm now on this fundamental point. I slowed myself down, okay? I'm changing the nature of this lecture. This is what I'm telling you because of the question. when the question is asked, I imagine that there could be also some other people that, and I want to make sure that you follow me, okay? So in the same manner, you see, if I have a large representation with one fermion, two fermion, and so on in this left-handed group, I don't know, just imagine it. The TA generators, that wouldn't be Pauli matrices. That would be some ugly thing that I don't want to even write if the representation is big. This meaning implies that hypercharge 1 is equal to hypercharge 2, precisely because I can rotate them around to the hypercharge of the last guy. That's very important. Okay. This is now we are building the standard model, which I thought of started yesterday. Will, however, I told you, will be more and more systematic. We'll try to be. And we said that there is an electromagnetic charge. When I say that the group of the standard model is SU2L cross U1 hypercharge, once again, that means that Q electromagnetic lives inside, and that means it has a piece which is T3. Let's write this hat, because T3 doesn't have to be Pauli matrix. Tomorrow you tell me, oh, maybe there is a triplet of fermions. Okay, suppose LHC says tomorrow there is yet another. So this is just generic. And by the way, T3 once again left is sigma 3 over 2. Where T3, just to remind you, right, is not Pauli matrix, is 0. The right-handed fermions are. Plus the generator. I normalize it with a half. I could put some coefficients, but it's useless because hypercharge is completely arbitrary. This equation you should read like this, that hypercharge is 2 Q electromagnetic minus T3. Why? Because this you know in your sleep. It should not happen that you don't know the charge of the up quark and down quark. You can't go on. You don't, physics, the beauty of physics, we don't have to know things. Okay, we can rederive them. That's the beauty. But every time we rederive it, it will drive you crazy. Some numbers I'm going to insist. These numbers you should know. And T3 you know when I tell you the representation content. If I tell you that the guy is a doublet, then you say, okay, it's Pauli. If I tell you it's a triplet, for example, for a triplet of fermions, F1, F2, F3, how would the T3 look like? What do I mean by this? Well, you know from spin in quantum mechanics, it has eigenvalues 1, 0, and -1, and so on. Okay. It means that hypercharge is a derived number. Okay, the beauty of SU2, remember, there was a fantastic thing of SU2 that you know the charges automatically, and they were quantized, which corresponds to the quantization of charge in nature, and now you lost it. However, now you cannot fail, okay? Here is the thought of a kind of characteristic of the standard model that we consider ugly. Charge is no more quantized, if you wish. Charge is arbitrary. Why? Because hypercharge is arbitrary. You see now what we learned, the charge, Q electromagnetic or hypercharge, why? They are arbitrary. So if you find a new particle with a different charge, Glashow tells you, no problem, I will fix the hypercharge, okay? This is now fixing, not predicting the charges. Standard model, per se, per structure, does not predict charges, does not correlate them even. Here is a statement to whet your imagination. There is something called the anomaly, axion anomaly, a profound concept in field theory. It turns out that the so-called gauge anomalies actually do a fantastic job of correlating quark and lepton charge. This is a side comment. This is not something I can teach now. At the end of the course, I'll say a few words. At this point, charges are arbitrary. But then, of course, we can be, however, in agreement with nature. And it's very easy. For example, I tell you ER. So someone tells me, what is the hypercharge of ER, please? Look at this formula above and tell me what is the hypercharge of ER? This formula.
-2.
Great, yes. And what about UR? Now that you are there, what is the hypercharge of UR?
4/3.
4/3. Yeah, you were saying I can be that. And if you tell me that there is a DR, Yukawa, I'm sorry for this slips. DR is what would it be? -2/3, right? It's twice the charge. It's very easy. It's just twice, the right-handed twice the charge. Now, what about these guys? Okay, let's now look at, okay, so this fixes the right-handed world, okay? And it's kind of ugly that you have to remember these numbers. Don't feel bad if you don't remember that. I'm never going to ask you. I'm never going to imagine that you remember this number. You just go back to the formula as you did. Okay, let's look at the QL. What is the? How would I find the hypercharge of UL? Help me. So look at the formula and help me with this with an asterisk. It's 2. What is T3? What is T3?
1/2.
1/2. Thank you. I need you to participate. We have to build the standard model together. I don't want you just to learn it. We got to. No, I made a mistake. It's not T3. I should first put the charge. What is the charge? It's 2/3 minus T3. And you just told me that it's a half. Thank you. You helped me. Let's imagine that I'm forgetful. So what is this number? Who is quick with the numbers? This is 4/6 minus 3/6, 1/6, 1/3. Am I right? Please check on me. Yukawa DL, Yukawa hypercharge. It's 2. What is the charge of the downport?
-1/3.
-1/3. Thank you. Minus, what is the T3? It's -1/2. Even I know this. What is the number now? It's 3/6 minus 2/6. It's 1/3. As I told you, it has to be equal. You should have told me, you're stupid. You're wasting your time. Why are you checking hypercharge of DL? They have to be equal. You just taught us, you gave us the reason. They must be equal because there is no up or down. I can interchange up into down. Very good. LL, what is the hypercharge of nu L? It's 2. Now we are getting better at this. It has 0 charge, we said, with great certainty, -1/2. And this is -1. Yukawa hypercharge EL, well, you're saying every fool knows they has to be equal. This is -1 minus -1/2. No, yes. And this is now again -1. They are equal as they have to be. This is what we have. We can always, now Gleshow cannot fail. Gleshow didn't like to do this because the beauty of the theory was lost. He took his time. He actually waited. He got his PhD. He spent bloody years of his PhD trying to make sense out of SU2, not giving up. I want you to appreciate the beauty of doing physics when you just don't immediately start doing what is called model building and start speculating and start saying, for example, it's very popular these days. Every Dick and Harry says that Einstein theory has to be motivated, okay? And it's absolutely not proven. It's never been proven. And some people will tell you that they have to add infinitely many particles to the Einstein theory. is done through what is called the string physics, okay? And it is not actually proven that Einstein theory failed, strangely enough. Because to prove that it fails, you have to make predictions and then show that they're wrong. That has not been achieved, okay? And here is an example of great physicists doing physics as they did in the past. The way Maxwell, Einstein, Newton, all these guys work. You struggle with the minimal, and only when you're sure that it fails, you do the thing of adding U1. Because you lost a lot. This is a bit sad. Charge is now not predicted anymore. You can be anything you want, anything literally, because you will choose the hypercharge appropriately. Very good. This is what I want you to appreciate. However, something nice will happen if you understand this. Now, the third step is now we want to study the interactions, gauge interactions. Of course, we have only gauge bosons. It's obvious that we are studying gauge interactions, okay? We found out yesterday, remember, that it's very easy that there was this interaction G over square root of 2. You went from the up to down. So, of course, it's the same for neutrino. Remember what I keep telling you. Please pay attention. This is very important, that neutrino up and down, it will always look the same. You don't have to remember separately, okay? Neutrino is up, electron is down. I could have one notation, W mu plus. I called it, and this was nothing very surprising. W mu plus was A1 minus IA2 of the SU2 gauge bosons, normalized. There is, of course, a minus. That must be in the anti-state. AIs corresponds to the generator TIs of the SU2. These are gauge bosons. These are generators. Gauge bosons correspond to generators. Very good. There was also some funny interaction, neutral, which we wrote. How will the neutral look like? Now I can write systematically. There will be F bar, gamma mu from the covariant derivative. There will be G T3. I'm going to get rid of that hat. I should really keep it. Plus G prime. Okay, let me just remind you, I'm sorry, just to be sure that you got it. It all comes from this interaction. It's a generalized Dirac. It's a gauge. It's a generalized. It's a covariant. Kinetic energy, Dirac Lagrangian. So it's I. Any multiplet, I call it F, gamma mu, d mu, F. And d mu is a derivative minus Ig, the SU2 coupling constants, Ta, A mu A, minus I, the coupling constant is G prime, the generator is Y over 2, and this is B mu. This is what we know, the form of the generators TA, this is what it is. And this will immediately give me the neutral interaction. I did the W separately. We call it neutral currents. Neutral gauge bosons, neutral currents interaction. Here we have F bar, obviously gamma mu, T3 times G, plus G prime, Y over 2. Sorry, A mu, 3, B mu times F. These are the neutral guys. A mu 3 and B mu are neutral. They carry no charge. A mu 3, that's our convention, corresponding to the Pauli Matrix sigma 3. There is one guy, which is diagonal. T3 is diagonal. It's either Pauli or 0. And B mu being U1, it's obviously diagonal. But what is Y over 2? That's Q minus T3. I don't want to write Y over 2. I don't know what Y over 2 is, okay? I just wrote you for once to have this funny number here, but who cares? So this becomes, so this is interaction neutral. neutron. This becomes F bar, gamma mu. What will it be? It will be T3, G A mu 3. Please check with me. If I make a mistake now, it will be sort of ugly. Minus G prime Q. Q is Q electromagnetic. Let me just write. Okay, Q is usual, is Q electromagnetic. Okay, there is just one charge at the moment, important. You agree with this? And then what is left is G prime B mu Q F. Correct? F can be anything. It can be left-handed fermion, it can be right-handed fermions. I don't have to worry about. I can read off the properties from T3 and charge. I know T3 and charge for every fermion, so I can write a universal form for neutron interactions.
Professor, the G prime Q has missing the B mu. Is missing the.
You where?
And the last expression, G prime Q has to be with B mu, the vector.
I wrote this nicely. You're
In
telling
the
us.
first term.
Oh, thank you. Yes. You see, it's good. Okay. You see, I'm reasonable. You tell me. I'm not going to fight you. You're saying I should put B mu. I put B mu.
Without the Q, I think.
No, what did I? No, this was A mu. What did I write? Oh no, forget it. I write something stupid. Let me try again. Maybe I'll do better. This is, what did I say? This is F bar, gamma mu. I want A mu, I want T3. Maybe it was correct. I'm sorry. G A mu 3. I needed to be sure for myself. Minus G prime minus G prime B mu. Am I right? Is this what you were trying to tell me? I think this is what you tried to tell me. This is the piece proportional to T3. And then there is a piece proportional to Q. Yes. Maybe this is better now. I don't know why. See, I told you that I need your help. I get up late. Sorry?
I think it's better now.
It's better now, thank you. It was good before, but this is better, right? A polite way of saying that I made a mistake. It was good, but this is better. Notice, now we say the following thing. We are saying that we want to reproduce nature. What does a scientist do? What does Einstein do? He says, I have to reproduce nature. I have to start with something, so I have to agree with Newton, says Einstein. And what does Glashow say? I have to reproduce nature. I have to agree with Maxwell and Schwinger and Feynman and these guys. Therefore, there is a photon, of course, which couples so that it couples to charge. That I have to reproduce. That immediately tells you that this particle here, look at the immediate consequence. It has to couple to charge and only to charge. The photon couples only to charge. Photon doesn't care if you carry T3 or hypercharge. It's just going to ignore you, snub you. Like neutrino carries hypercharge. You see, go up and you will see that neutrino carries hypercharge. Photon doesn't give a damn. Photon says, well, you don't carry charge. So that tells you immediately that this particle here is not a photon. A particle that couples to T3 must be a new gauge boson. Does everybody appreciate that? This is what Glashow says. There is also a Z boson, Glashow says. And Z is not the photon. that I called A. And what is the Z boson? Let me write it down. It must be this, says Glesher, G, A mu 3, minus G prime, B mu. And it has to be normalized. Remember, I like to normalize my fields, so I'll just normalize. I just predicted two beautiful things. One, that there is a new gauge boson. Two, that it has a universal form, its couplings. Everything will now follow, okay? But I want you to appreciate that there is this Z boson. And I know immediately who the photon is. How do I know? I know that because the Z boson must be orthogonal to the photon. It has nothing to do with the photon. These are independent gauge bosons that have independent interactions, so they are orthogonal to each other. So what is the form of the photon? It must be G prime A mu 3, must be orthogonal to the other guy, plus G B mu divided by G squared plus G prime squared. You understand what I've just done? It is orthogonal. Now this ensures that it's orthogonal. It must be orthonormal. I want it normalized. So I found something really special. I already, just from the fact that I claim that there must be a photon, I realized that there will be a new gauge boson, and I know its form. This is the fundamental result of the standard model. This is the first great prediction, okay, that will make us, people that arrived in the 70s, fall in love with the theory. And especially when the Z bosons interactions are discovered through neutral currents. And it will take some time. In 1983, the Z boson will discover, okay, it will take some time. Z is 1983. Z and W bosons discovered. We'll talk about that later, okay? Not at the moment, okay? Any questions here? In order to simplify this ugly notation, I'm going to introduce a weak mixing angle. I will introduce the ratio, the mixing angle, which is the ratio of these two couplings. Remember what I said, the standard model is a not true unified theory. The couplings are different. There is one parameter that I cannot predict. So let's write it. We can write it nicely. A mu, like first like the photon, which I like more, is, what is it? Sine theta W, A mu 3 plus cosine theta W, B mu, obvious. And Z is orthogonal. What is it? It's cosine theta W, A mu 3 minus sine theta W, P mu. Why? Because it's obvious from this relation here. This relation here is another fundamental relation of the standard model. Obviously, sine theta W is G prime over square root of G squared plus G prime squared. This is sine theta W. To remember, then cosine theta W is just, of course, related. I don't even have to write it, okay? This is whatever you want to remember. Whether you want to remember sine theta W, tangent theta W, it's up to you. But now I know the forms. Therefore, I predict my interaction, the neutral is, what is it? Let me go up. It looks like this. It looks like, because I normalized, it looks like G squared plus G prime squared here. No, I want to write maybe more elegantly. I want to take F out. This is universal, gamma mu. Then I have square root of G squared plus G prime squared. T3 Z mu. And then there was plus G prime Q and B mu. And what is B mu? I go here. This is the fundamental relation. I just read what B mu is. B mu is minus sine theta W. B mu is this coefficient. All I have to do, Z mu as a function of B mu is B mu as a function of Z mu. This is a SO2 orthogonal transformation. Please check it if you don't see it immediately. Z mu, but you should know this by now. Reversing this equation actually is taking the same coefficients plus cosine theta W A mu. This is my fundamental interaction, which is F bar gamma mu. The first term is G over cosine theta W. T3 minus G prime sine theta W Q. This is E boson plus G prime cosine theta W Q A mu. Any questions, please?
I have one question, Professor.
Yes, please.
When we define photon as an orthogonal state with respect to Z boson, how can we see that it's massless from this definition?
We cannot. I cannot. This is a generic problem, of course, of theories. Basically, almost all theories. You normally never predict the masses. You know, it would be fantastic if we predict the masses. It actually turned out that in the Higgs mechanism, a miracle will happen. You and I will be able to predict the mass of the photon to be zero. By this point, not. Glashow says, I know there is a photon. Glashow cannot predict the existence of the photon. Remember how I started? I didn't say that Glashow predicts that there is a massless photon. He says, I was told, he says, by Mr. Maxwell, and the theory was developed by these other guys, that there is a photon and it couples to Q. I should have said also, okay. I didn't, because I'm not talking about masses, of course, MA is zero. He says, well, you know, if you tell me that it's zero, it's zero. Glashow doesn't care, really. If you make a measure tomorrow, by the way, and it's not zero, Glashow has no problems. Maybe the mass of the photon is 10 to the minus 22 electron volts. Okay, says Glashow. Just take it to be 10 to the minus 22. Glashow is not predicting the masses because he doesn't even know how the symmetry is broken. Masses break the symmetry. We'll talk a lot about it. All he is predicting is interactions. Glashow says, I'll be coming back to this point. I believe that there is a gauge structure in the interactions in nature, and I'm going to tell you how the interactions look like. He doesn't even have the reason to say that there should be a gauge principle. This is, you know, he's taking the approach of science. There is no better approach. There is nothing you can do, says Feynman. Feynman says, one of the greatest spokesmen, if not the greatest, in the history of science in general. Okay, I hope that from time to time you watch the videos of Feynman, because you will learn more than anything else about the logic and the process of doing physics. Okay, Feynman says, make a guess. I don't care what your guess is. Make it coherently. When I say a guess, idea, whatever, you just do it. Make a guess, please. 1, 2, compute. That means you get predictions. So he says, if 2 is no good, you cannot do that, then stop. Shut up and please don't publish any papers, okay? I hope you remember this thing, okay? Because it's not what is done by the most of the physics, which is coming from the strings or whatever. You're saying, I can't make predictions, that's why I have to go on. And I'll go on year after year because I have a fantastic theory. This is the best theory in the world. The reason I cannot make prediction because it's hard to make predictions. No, says Feynman. You have no right to say that. You have to make predictions in order to speak about it, okay? And Glesher says, I'm making a guess that the gauge principle is good. I don't want to debate with you, and I'll make the predictions, and the predictions are the above, okay? Now, some predictions will emerge, some will not. So Glesher cannot say what the masses are, but he can say what the interactions are, and he does it in a beautiful manner. Let's put it here. Let me just finish, okay? So Glesher says, 1, it's a gauge principle. He's talking about weak and electromagnetic. Later, some people will do it for strong. It's not Glesher. Gauge principle says interactions follow the gauge principle. And then 2, I will give you a number of things. 1 is neutral current. This will be the first great prediction, okay? Then we'll talk about other things that may emerge. So we said once again, so alpha L interactions neutral is F bar, gamma mu. Then there is a Z boson. Notice that I know what G prime is. Just to remind you, G prime is G tangent theta W. So it's very easy. So what I get is very easy to see. Z boson couples with a strength G over cosine theta W. I will take as a common factor. And then I get T3. There was T3 here. And G prime sine theta W give me sine squared theta W. Because G prime has an additional sine theta W hidden in tangent theta W times Q. Here it is. It has a universal form. We just found that the Z boson has a universal form, just like the photon. You can predict any neutral current process with one parameter. If you guys give Glesher theta W, he can predict any scattering in the world you want. He can scatter neutrino on the up quark, neutrino on the down quark, electron on the up quark, electron on the down quark, electron on the proton, electron on the deuteron, whatever. I know all the T3s and Qs in the standard model from the structure. There is, of course, another important interactions, which is electromagnetic, coupled to electric charge, coupling constant E, F, A mu. I can put it outside or inside. There was F here. So I did separately. So why don't I just do without brackets? Okay. Plus photon. What it means, notice that G prime, look at this interaction here. GE is G prime cosine theta W. This is just now a definition of E, because the photon I'm talking couples to something that I call electric charge. I derive it from here. G prime constant theta W. I got the form. By the way, I want you to pay attention to what I'm doing today. This is very rare. Most of the books claim that it's Weinberg that predicts in Salam the form of these interactions through the Higgs mechanism. Absolutely wrong. I don't need any Higgs mechanism to prove the interaction as I'm showing you. This is of course equal to G cosine theta W. Notice, please, that E is less than G. In other words, weak interactions are not weak at all. They are stronger than, look, coupling is bigger. Weak is actually stronger than electromagnetic. So why do we call them weak? Because electromagnetic at low energies, it has to do when Q is much smaller than MW. Then of course, I just have the propagation indirectly. The photon goes as 1 over Q square. And the W goes as 1 over MW square, we said from the propagator, okay? Q is going to be small. When I say the Q is very small, just imagine it's going to 0. Then, of course, the only thing is MW1 and W squared. So by definition, of course, here, this will be rather weak. It's weak because I took a funny Q. But if I take Q much bigger than MW, then, of course, here is the photon, 1 over Q squared. Photon, I want a small picture, so this is clear here, and the W here, some other scattering through W. This will be now basically 1 over Q square again. Why? Because there is always 1 over Q square minus MW squared. When Q is very big, it's approximately 1 over Q square. I'm just ignoring the MW square and so on, the small numbers here. So in this case now, weak is stronger because G is bigger. This will go as Z squared, this is G squared, E, G, G. So in this case now, weak is stronger. A bit, not much. Depends on this mixing angle. But strictly speaking, it's stronger. Okay? This is important. Okay. The beauty of the gauge theories through the messenger is that the strength of the force depends at which energies you are. So you have to rethink about what you know. You have to keep this in mind always. You know what I suggest? We could first tell me if there are questions. If not, I needed to finish on a thought, and it's always good for pause for me to think whether I'm going with the right pace, and for you guys to, you know, I know you could go on, but I strongly suggest let's meet in now it's 12:03. Let's meet at 12:10 again, and please try to think if there is something that I stare at this and think if there is something I didn't do right or confuse you. Or okay, so we are back at 12:10 in 7 minutes. Okay. 12:10. We are back. Any questions, please? I told you, those of you that may feel that you lack any pre-knowledge, please ask anything that may or may not be related with the detail that touches upon the this sort of neutral current processes. We call these neutral currents because they are currents and they are neutral, right? So what we are saying, why neutral? What is the name of neutral current? Well, one is a photon. Photon couples to J mu, which I could call J mu A, which is A mu, J mu Q. Sometimes one writes electromagnetic, or no, maybe not. This is not, why not just electromagnetic? And you know that J mu A, you can write universally Q electromagnetic, which is QF. This is the beauty of the QED. This is assumed at this point, assumed in Glashow's work. Remember, he assumed that there will be something proportional. Sorry, the way I wrote, why don't I put a coupling here? Of course, there is an overall coupling. There is similarly a G. The coupling was not G, but G over cosine theta W. It came out because of the normalization of the Z boson. Notice it's even a little stronger. It's interesting how the Z boson couples even more strongly. This coupling is even bigger than G. Okay, this is interesting. The W coupling was G. This one is even bigger in general. And then what was it? It was Z mu. I can write J mu Z. I can write simply and elegantly. And the beauty of the gauge group standard model approach is that this is basically universal, just like the current. It's like the photonic current, the Z current. It's just gamma mu. A little more complicated. It has a charge piece. It has two pieces. So how do I read this? By the way, in the books, you will see also in the books written like this. L is the famous projector, 1 plus gamma 5 over 2. You will find in the books. So who is right? Me? I didn't write this L, or the guy who puts this, or gal, this L? Is there a difference between these two? Anybody wants to comment? The point is that T3 on acting or right-handed fermion is 0. Therefore, it's the same. And T3 acting on the left-handed fermion is this famous sigma 3 over 2. So it is irrelevant whether whether you include it or not, L, because L acting on right gives 0, but T3 acting on right gives 0 anyway. L acting on left gives 1, and that's incorporated. So these are now identically equal in the structure of the standard model. Don't be confused by this L. So see, all you need to know is, if you know theta W, it is all predicted. All the processes that you can imagine. Why? Because G is E over sine theta W. And I know that E is a square root of 4 pi alpha. I know it, this number. You tell me what alpha is, I know what E is. From E, I can compute G, so I can predict all the processes in the standard model, all of them, just with one parameter. And you should know that sine squared theta W, you probably know, is 0.23. It's very close to a quarter. In other words, theta W is basically 30 degrees.
Sorry, Professor.
Yes.
Yeah, the expression you wrote, E equals to 4 pi alpha. Is it related with the fine structure?
Yeah, this is called the fine structure.
Okay.
This is just the name that we call. And this is the famous thing, you know, that you often are told that alpha is 1/137. By the way, this is only true when exchange momentum is very small, 0 compared to the particle physics units. We'll talk about it in the time to come a lot. But this is what the experiment measures, is this alpha, and then I can compute E. By the way, from here, E is roughly a third. It's not a very small number. And I think that G is about 0.6, I think, roughly. You can check it. I don't remember it so much. Let me put a little question mark. It's not so important because it's a derived quantity. I don't have to remember what it is. I don't even have to remember what E is. I can always take a square root. And typically you will remember alpha, the fine structure, which measures the electromagnetic strength. And how do I read it when for example, if I have to think like this. I cannot think of an up quark. I have to think of the right-handed up quark. You know, if I now I'm interested in the J mu Z. So how do I interpret this? How does, for example, for the right-handed up quark? Well, right-handed up quark, it's easy. I go back in that form. So I would have UR bar, gamma mu, T3 0. I'm sorry. T3 0 minus 2/3. I could put the value for sine squared W, but I will just keep it. Sine squared W. This is the way, this is the current J mu Z on the right-handed up quark. And if I wanted right-handed down quark, then it would be dr, gamma mu, 0 again, plus 1/3 because the charge is negative with the same theta W and so on and so forth. And if I ask you, well, what about, I don't know, nu L? Well, you will tell me there'll be nu L bar, gamma mu. T3 is 1/2, charge is 0, nu L. Notice it's purely left-handed. It's very interesting. Just like the charge current, it's purely left-handed. But EL, for example, would not be like this. It will be like minus 1/2 here, plus charge is negative, sine squared theta W, completely different EL. And so on and so forth. I'm not going to write, you can reproduce them. All you have to know that all I need to know is theta W. Okay, what else can we say? Any other question, please? We have derived, you know, at the very beginning, we have derived. We'll have to go back and learn what we have derived. We have to study it. I'm going to now teach you the physics of the massive gauge bosons. We'll be studying things like W decay. You know, we will go through parity violation because in nuclear physics, it's very complicated to see it. I'm going to make you go through and this may help some of you that don't know much particle physics. I will actually go through some nitty-gritty of particle physics to appreciate what this model is all about. But I wanted to show you how you and I could sort of get the essence fairly quickly once you get an idea. This is one of those great developments in physics when idea is everything. Predictions just fly out. Okay, it's not the same when you study Einstein theory. Gravity, if you know, fundamental prediction is what happens to the Mercury perihelion. That's a long calculation or deflection of light in the sun that you have to work out. But you can do it. Here it took us basically, 20 minutes or something to arrive the most fundamental prediction. Okay, the neutral currents in the 70s, what emerged, that there was a perfect agreement with experiment. And eventually, as I said, there was a direct search. Let me just see the W and Z. The search is at CERN in the PP bar machine. SPS, it was called a synchrotron, whatever its names, I don't know. It's a P plus P bar machine. It had a circumference about the 7 kilometers. You can go running around it, okay? It's very small compared to LHC, we'll come to that. He started it in late 70s. The machine was finished in 1983. They are found in this P plus P. Why? How do you do it? Well, inside P, there are quarks, like up and down quark. And P bar, there is U bar, D bar. So for example, I can have a scattering, say the enters down quark, enters from P, enters, say, anti-up quark from P bar. And what will it produce? It will produce W minus, if I have enough energy. And that's how it was seen. How will I know that I've seen the W boson? By the way, it's not stable, W will decay. Well, it will decay. I'm gonna study this decay with you into, say, an electron and a neutrino. So when I say that anti-up quark enters, remember really what I'm saying, that the up quark is going out, but I will be schematic. I'm not supposed to break fermionic lines. But when I take the anti-particle, it's okay. Charge is conserved in this picture, okay? So I could say that neutrino comes in or anti-neutrino goes out, it doesn't matter, okay? Okay, I emphasize here left-handed, it's not so important, the chirality, it's important that you see this, okay? And we'll see how this we will do very, very carefully, as if you didn't have a particle physics course. We will compute it in detail, the properties of the W decay, just to show you how you find it. What was learned that MW was a mass about 80 GeV. Well, we can just write. And similarly, of course, you produce the Z boson, take down an anti-down quark, and so on. I don't have to tell you that. MZ is 90 GeV. Klesho couldn't predict them. Klesho is just said, you will find these guys, I can't tell you what the mass is. And what we learned that they couple, it's not just finding this particle, of course, it's making sure that they couple the way they couple, okay? And that means when they were discovered in the 80s, a new machine was built. The next step was LEP. This is large electron-positron EE-BARM collider, LEP, had an energy in the center of mass of 205, I think, roughly, GeV. This will be very important. We'll talk about it. It's very important. This machine produced billions of W and Z. This became a WZ factory and established a standard model as a high precision theory. It measured the width of the W, carefully the width of the Z boson with a fantastic precision, and so much was learned about individual channels that through the lab, standard model becomes a high precision theory. That's the task ahead of us. We have a lot of things to now go to. We have to understand the physics of the gauge bosons, the way to search for them, the way to interpret them, the decays and so on. But we have to understand the question that you asked me today. How do you know that photon is massless? Can you say anything about it? Can you predict the W mass? How do particles get masses anyway? What are you saying here? Okay, notice maybe it's the right moment. It's even more maybe interesting to say it in the case of fermions. I have probably a lot to say here. I'm not sure if there are things that, by the way, you know, LEP is huge. LEP, this little thing had 7 kilometers, right? It's a little circular machine. Here we have a big circular machine, E bar. This is LEP. Now the circumference is 27 kilometers. This is the same tunnel as the LHC. Okay, already LEP was this huge thing. It goes under little villages at the border between France and Switzerland near Geneva. That's CERN, as you know. This is old CERN. Okay. What we have to talk about are masses. What about masses of these particles? I have established the interactions. And I'm just asking you to believe. We'll study how much that the standard model agrees perfectly with the experiment. Okay. This is a great problem of what you and I are facing, especially you young guys. It would be much nicer if you started to disagree so that we discover new things. So when people speak of the problem of the standard model, unfortunately, there are no problems. And that's the problem, because we like problems. We want to discover new. So in order to people to say that they are doing something new, they say that there are problems, that they pretend that there are, so that they can solve the problems that are not there. But we'll talk about it a lot. So what about masses? For example, let's talk about fermion masses. Let's talk about the electron mass. I have my symmetry, remember? It's SU2L. I have to respect it. According to the gauge principle, there is a symmetry I have to respect. Well, not just gauge principle, even globally. If the symmetry is to be local, it has to be global. Okay, I have to respect the symmetry. This is the standard model. Now, I will write, what is it, what I have to write down? I have to write down, I'm sorry, I have to write down the mass term of the electron, which has this form, psi bar E, psi E, which I will often write as ME, E bar E. I have too many particles to write. But E, what is E? E has both left-handed and the right-handed component. EL is L times psi of the electron. Let's just imagine that I wrote in this notation, if you wish, and write psi of the electron. Okay, so the mass term, the mass of the electron, ME, E bar E, it's trivial to see because of the properties. E dagger has gamma 0, which anti-commutes with L. This is actually EL bar, ER. EL bar EL would be 0 because of gamma 0 plus ER bar EL. This is the mass term. As you know, from the Dirac equation. So my question, can I write this mass term? This is the central question. Can I write this term with the symmetries of the standard model? Remember how the standard model looks like? There is a doublet nu EL, and then ER. Can I write the above term? Someone wants to help me? We are building it together.
I think no, because there is a mixing between left and right.
Yeah, precisely. There is no left-handed electron. This is just a name. The way I wrote it here, there is only the thing that exists is this. Particle inside, I can move them around by the SU2 transformations, okay? There is only a doublet, there is not a singlet. So the only thing I could write would be LL bar. I have no right to break the doublet. The doublet is there, times ER. I can try to write this. But this is Lorentz invariant, of course. Let's check the symmetries. Lorentz checks. Just like the above, left-handed, right-handed, this is perfectly okay. But what about SU2? No, this breaks SU2L. Because I have a doublet times a singlet, that remains a doublet. How could I make this invariant? Oh, by the way, okay, before I go on, okay, a few more minutes and then we are done. Well, I still have a little time. We had a break. You can now say to Gleshow, but why the hell are you bugging us with this symmetry? Now you are telling me you cannot even write the mass term, but the electron is massive. Now Gleshow is not completely stupid, if I may paraphrase Pauli. So what Gleshow wants to tell you is the following. I believe in the gauge principle as something which is valid at all energies. My interactions are universal. He says, remember, the mass term, he says, I mean, what is the mass term? Mass term is something that actually depends on energy, because the relation that I have, that Einstein taught me, is this one. E squared is P squared plus ME squared. So for example, in the case of the electron, okay, let's take the electron like this. And if P electron is much bigger than ME, then this is equivalent to ME basically being zero. He says, when you go to high energies and you want to probe my theory, the masses become less and less important. So you can actually probe my principle. I know it looks stupid what I'm doing, and I'll just write the mass term. So he said, I'll break the symmetry. And he says, I'm breaking the symmetry. So what Gleshow does, he says, I will write EL, ER. I will write ME like this. That's what Gleshow does. Because I'm willing to break SU2L through this mass term. However, that breaking is kind of soft. We call it soft breaking. What does it mean? The higher the energy, okay, what it means, if energy goes to infinity, if it grows, okay, just imagine the infinity is just very large at LHC. E goes to infinity is equivalent to mass going to zero. After all, the energy at the LHC in the center of mass is in TeVs. We'll talk about these numbers, okay? This is about 10 to the 6 masses of the electron, okay? Electron is basically massless, so he says, allow me please to break it. You and I will learn, however, that there was a pending catastrophe. It won't work. This nice and Gleshow was turned out that you cannot work masses. If they break symmetry, they destroy your normalizability. This is highly profound and surprising. And people had to come up with an alternative, which is called the Higgs mechanism, okay, which is one of the greatest revolutions in particle physics. So you and I are going to take the symmetry more seriously than Gleshow. It's easier for us because Higgs, Weinberg, Salam, and others prepared this at Hof later on to understand how to work with the theory. And we are going to say that we want to have a symmetric mass term. Now, how can I complete this to be symmetric? Tell me. And I will let you go, basically. I'm almost there. If you tell me, how can I from here make this SU2 invariant? What is missing? I need to make it SU2 invariant, and it should stay Lorentz invariant. So let's go back. Now you and I, however, I have to say, however, breaking, Glesher didn't know it. Well, he was afraid that he could do bad. I mean, I'll tell you a little more. Breaking is no good. We are not allowed to break the symmetry. Just trust me. We have to have, in other words, must have, really must, just like Lorentz. I don't know how to work if I break Lorentz symmetry. I don't know how to work if I break SU2 L cross U1. So once again, I have LL bar, ER. How can I make this SU2 invariant? Group theory. If you have a doublet, how can you make it a invariant? You have spin half. Remember, imagine that you have some doublet D. Any doublet transforms. Remember what I said? D goes, D is a doublet. D is a doublet. So what I mean is that trivially, okay, these transform. How do I get a doublet? Actually, I may have more than, I may have many of them. Well, 2 is enough. How do I get a singlet? Well, I should take D1 dagger, D2. You agree? You should be telling me this. I should not have to ask you, because this goes into U dagger, U D2. This is what you've done in quantum mechanics. This is what you learn in your group theory. In order to get a singlet, you have to take doublet and anti-doublet. This is invariant. Sorry, not bar. Well, for fermions, it's bar, because you had some, whether it's you know, for fermions, D dagger goes actually into D bar because of Lorentz, okay? It's just the Lorentz piece gamma 0. After all, D bar, F bar, well, I don't have to write this, you know. So in order to get a singlet, I need to put another doublet here. You agree? This is my D1, let's call it. This is my doublet D1, LL is D1, let's say. It's a doublet under SU2. It's also some funny guy under Lorentz, but Lorentz is okay, that I've checked before. So I must put here a doublet, you agree? D2, another doublet. Is that clear, please? I hoped some of you would tell me, because there is no other way I can get a singlet. I can never get a singlet out of doublet and the singlet. I need 2 different doublets. Okay. So what could be his doublet? What can you tell me about this doublet under Lorentz? Now I know it's an SU2 doublet. So D2 under Lorentz symmetry. It's what under Lorentz? Is it a spinor, vector, scalar? What is it? Lorentz what?
It's a spinor too.
It's a spinor. Look, I just said that LL bar ER is Lorentz invariant. The only way to make an invariant out of spinor to take the spinor and anti-spinor, which I've done here. What if I put a spinor here, another spinor? Spinor means that they carry spin a half, or or minus a half, it doesn't matter, plus or minus half, plus or minus half. If I put another spinner, I will have 3 times spin half. This can never be invariant. It's already invariant, I said. This is Lorentz invariant. This is the crux of the whole point. I've already achieved Lorentz invariance. This is exactly the same thing as EL bar ER. For Lorentz, Lorentz doesn't care. This guy doesn't care whether we are doublet or singlet of SU2. You must think separately of symmetries. For Lorentz, SU2 doesn't exist. They commute. For SU2, Lorentz is a separate thing. So the first thing that I've learned here, D2 cannot be a spinner. Why? 3 spinners can never get spin 0. Okay, how can out of half? Remember how spin is built out of spinners, right? You have plus or minus half, plus or minus half. 2 of them, of course, can give me 0, because I can take minus a half, plus a half is 0, or plus a half, minus a half is 0. But if I take 3 of them, if I add here plus or minus half, then of course, all I can get is plus or minus half, if I already took a 0. Or if I take 3 times, I can also get plus or minus 3 halves and so on. You know, I can build them, but no 0 out of 3 of them. So if it's not a spinner, what is it here?
Scalar.
Scalar, precisely. What I can do, I can write the following interaction. LL bar. I put a doublet of SU2, by the way, it's a scalar, but it's a doublet, ER. This is called Yukawa coupling, historically. I won't tell you now today. So there is some coupling that I call the Yukawa coupling for the electron. Of course, there must be Hermitian conjugate term, Lagrangian Hermitian. This is a scalar doublet. It has a name. Someone knows the name for this doublet? It's quite famous. It's the most famous particle in the world.
Higgs field.
There is nobody. You go ask, you know, go to the party, meet anybody party, go to your cashier when you go to eat, and you will see that they all know about the Higgs doublet. There is a Higgs doublet here. Inside there is a Higgs boson, and the rest of the course is going to be quite a struggle to learn this. But you see, I just wanted to tell you, I'm going to be forced to put a scalar particle, even if I don't know anything. Now, nothing about field theory. If you tell me, someone tells me, I don't know who she is, at Hoft, for example, has, you can't break the SU2 symmetry. I'm very sorry. I'm not allowing you to break SU2. If you want me to show you how to make predictions, I have just came up with the fundamental prediction that there must be a new scalar set of particles, which is called the Higgs doublet. Because of doublet, you will see, oh, there's going to be a number of them, 2 complex particles. In other words, 5. Notice how the 5 is, just to show you. It has the following decomposition of charges. It has a charged particle and a neutral particle. It's a doublet. How do I know that? Well, LL bar phi ER is nu L bar phi plus ER plus EL bar phi 0 ER. Obviously, the charges must be 0 and plus. This is charge conservation from Q conservation. I even know how the, and I can write this as I can write this as some, well, I can just write it as phi plus. I can keep the neutral guy we like to call, people like to write as real plus imaginary. And in general, I could even include a constant here. For all that I know is, you know, this constant V, It's called the vacuum expectation value. And what it means that even when the value of the whole fields is 0, you're always building around 0. In the vacuum, there are no such fields. Phi plus is 0, H is 0, G is 0. This is called a vacuum. Vacuum should have nothing. But you're saying in principle, there could be some constant value. You know, there could be some energy floating around because this is a scalar. So it's okay. I'm not going to break Lorentz symmetry of anything if I give this guy how to achieve it. It's an extraordinary thing. Imagine, however, that it's true. And then all of a sudden you get Yukawa electron, V, EL bar, ER, plus ER bar EL. And this looks like a mass term. This is how it's going to work. I want to finish on this note. Of course, I'm not teaching you anything here. Please don't feel frightened by what I said here. Even if you didn't understand anything, even if this all escaped you, please don't feel bad, because this is what the next, 20 lectures or whatever I have to give will be all about. I just wanted you to see how the symmetry can play such a profound role that we will go beyond the theory of weak interactions and create a theory of the origin of mass, which starts with this celebrated Weinberg paper, the next milestone in development of the Standard Model. This is what the Standard Model will be all about. I stop here. Any questions, please? Comments, anything? It doesn't have to be about the lecture, because I mentioned something which is obviously beyond the lecture. Okay, the last part was not a lecture. The last part was anticipation. You have to be systematic about this. You know, before I do this Higgs mechanism, I will first try with you to understand what the mass of the gauge boson really is, how we probe it, how does the massive gauge boson propagate, and so on. Then we will worry about how to generate a mass, which should be symmetry breaking. We are going to spend some time next few weeks doing field theory, much more than the Standard Model physics. We will have to be patient. But please, if you have any urgent comment, it's your chance now. Oh, one thing, please, before we stop. I was told that you guys have nothing on Wednesdays. I thought. Now I'm told that you actually have a class on Wednesdays. What is going on? You have a class tomorrow?
Yes, we have.
So, and what about Thursday? No clue. Today. No, today is Wednesday. I'm confused. I'm sorry, not tomorrow. You have a class today, right?
Yes.
So we cannot do my office hours, because I thought you guys told me that you didn't have a class. The Wednesday was ideal. Anyway, what about tomorrow? What's the schedule tomorrow for you guys? Afternoon.
We are free from 2 until 4.
So it's the same way that we do it on Wednesday and Thursdays. You agree? You agree?
Yes.
So let's do it tomorrow, if it's okay with you guys. If you have any question, I'm going to send you an invitation on Zoom to meet tomorrow at 2 o'clock. We don't have to, use the, ICTP recording for this. Okay, this is something informal. We don't even have to. We shouldn't probably record this, because you want to be able to ask any questions that comes to your mind, that maybe want to show me that you don't know, things that you should know. So let's do it tomorrow at at 2 o'clock. And then we'll think about maybe, so what about Tuesdays? How are your Tuesdays afternoons?
Yeah, there we have a class at 2.
Okay, so basically every day is the same. What about Monday afternoon?
That's free.
Ah, so Mondays would be best, maybe. You agree?
Yes.
Okay, so we'll do it on Mondays. However, I will invite you tomorrow just so that you have been asking questions and not wait for Mondays. Because Fridays, I have a problem on Fridays. I couldn't give you enough attention. Okay, let me think what good time. So any time is good on Monday. Let's just sleep on it. We can decide it later. Okay, okay, very good. Guys.
Thank you, Professor.
Sure.
Thank you.